IPv6 addresses and interface and the identifiers. In addition to being longer than IPv4 addresses by a factor of 4, IPv6 addresses also have some additional structure. Special prefixes used with IPv6 addresses indicate the scope of an address. The scope of an IPv6 address refers to the portion of the network where it can be used. So there is a special prefix used in this 128 bits called a scope. So it refers to the portion of network where it can be used. Important examples of scope include node local. The address can be used only for communication on the same computer. So that's node local. Link local, used only among nodes on the same network link or IPv6 prefix. So these scopes or the portion of the network could be node local or link local. So for node local, that's in the same computer. For link local, nodes in the same network link or IPv6 prefix, or global, internet-wide. For link local IP addresses and some global IPv6 addresses use interface identifiers or IID as a basis for unicast IPv6 address assignments. So for the link and global, they use IID in that 128-bit as a basis for a unicast address assignments. IIDs are used as the low order bits of an IPv6 address in all cases except where the address in all cases except where the address begins with the binary value 000, and as such they must be unique within the same network prefix. IIDs are used as the low order bits of an IPv6 address in all cases except where the address begins with the binary value 000. So these interface identifiers or IIDs are used as the low order bits of an IPv6 address in all cases except where the address begins with the binary value 000. So that's the only exception. And as such, they must be unique within the same network prefix. So these must be unique within the same network prefix to be able to distinguish these unicast addresses in link local, which is the same network. IIDs are ordinarily 64 bits long and are formed either directly from the underlying link layer MAC address of a network interface using a modified EUI format, EUI64, or by another process that randomizes the value in the hopes of providing some degree of privacy against address tracking. So again, IIDs are ordinarily 64 bits long and are formed either directly from the underlying link layer MAC address. So this RID came directly from link layer MAC address of a network interface using a modified EUI-64 format, or by another process that randomize the value in hopes of providing some degree of privacy against address tracking. So see chapter 6 for that. But usually, I mean, these are the two ways for providing these IIDs or 64 bits in this IPv6 address. So here's what it looks like. In IEEE standards, EUI stands for Extended Unique Identifier. EUI-64 identifier starts with a 24-bit Organizationally Unique Identifier, or OUI. These are the OUI, the 24 bits within this 64 bits. EUI stands for Extended Unique Identifier. EUI 64 identifier starts with a 24-bit organizationally unique identifier, followed by a 40-bit extension identifier assigned by the organization, which is identified by the first 24 bits. So this OUI identify this, or define this, how these bits will be assigned by the organization. The OUIs are maintained and allocated by IEEE Registration Authority, IEERA. So this 64 bits unique IID actually has the EUI 64 and then EUI 48, and the OUI for that is defined by IIE Registration Authority, IEERA. EUIs may be universally administered or locally administered. In the internet context, such addresses are typically of the universally administered variety. So again, EUIs may be universally administered or locally administered. In the internet context, such addresses are typically of the universally administered variety. So this EUI for IPv6 in the internet are usually locally administered universally rather than locally. Many IEEE standards compliant network interface like Ethernet have used shorter format addresses, 48-bit EUIs. So other standards use 48-bit EUIs, but it's rare. Usually it's EUI-64 for IID, and then the OUI as well, and then the assigned by organization bits. So they have used shorter format addresses for the 8-bit EUIs for years. The only significant difference between the EUI 48 and EUI 64 format is their length. See figure 2.7. So as you can see, they have different length: universal or local, individual or group. So that's the U part for universal, and G for individual group. So the EUI 48 and EUI 64 formats defined by IEEE, these are used within IPv6 to form interface identifiers. So again, these are used within IPv6 to form interface identifiers, or the IID, by inverting the U bit. So these are the U, the universal or local. So these EU64 and EUI48 are used within IPv6 128 bits to form the interface identifier by inverting the UBit. So it is used to form this IID, which is the basis for unicast IPv6 address assignments. IID are used as the low order bits of an IPv6 address in all cases except where the address begin with 00, right? So IIDs are ordinarily 64 bits long. So this EUI64 and EUI48 using its UBit are used to be able to transform it to IID, which is 64 bits long. Which is actually formed either directly from link layer MAC address of a network interface using a modified EUI64 format, which is this, or by another process that randomizes the value. So these 64 are formed using this EUI64, right, to convert that to IID. So this EUI64 identifier that used to convert to IID start with a 24-bit organizationally unique identifier followed by a 40-bit extension identifier assigned by the organization, which is identified by the first 24 bits. So as you can see, it's still this EUI-64 has 24 bit for OUI and a 40 bit assigned by organization, which follows the 64 bit IID for this IPv6. So this assigned organization also defined by the first 24 bits OUIs. So the OUIs are maintained by IEEE, and then EUIs may be universally administered or locally administered, but for the internet usually these are defined by the internet provider, locally by internet by IANA or IEEE. The OUI is 24 bits long and occupies the first 3 bytes of both EUI48 and EUI64 addresses. So it's the 3 bytes. The OUI 24 bits is actually 3 bytes because remember 8 bits is 1 byte. So the low order 2 bits of the first bytes of these addresses are designated the UNG bits. So the low order 2 bits of the first bytes of these addresses, so this within this first 3 bytes, are designated as UNG bits respectively. The U bit, when set, indicates that the address is locally administered. The G bit, when set, indicates that the address is a group or multicast type addresses. So if it's G, it means it's a multicast address. If it's if it's G, it means it's a group address or multicast. But if it's U, it means it's locally administered. Unlike universally. To distinguish that IPv6 128 bit within the network. Remember, this is still for link local IPv6 addresses. So that's the assignment for within the network. So for the moment, we are concerned only with cases where the G bit is not set. So we're not concerned with the multicast because that's a more complex one. An EUI64 can be formed from an EUI48 by copying the 24-bit OUI value, which is this, from the EU48 address. So we just the reason also why it's only 48 is because we can just add 24 to make it 64, right? hold on, 48 plus 24. No, that's not actually right. Basically, it will form kind of like the EUI64 address. So it placing the bit value 11111110 or hex FFFE in the fourth and fifth bytes. So again, an EUI6 can be formed from an EUI48 by copying the 24-bit value from the EUI48 address to the EUI64 address. So we're copying the OUI here to this 64 address, placing the 16-bit value, which is the 2 bytes, in the fourth and fifth bytes of the EUI64 address. So the 2 bytes are placed in the fourth and fifth here. Remember that's the first 3 is here and the fourth and fifth is after that the OUI. And then copying the remaining organizational assigned bits to form the 64, since there's assigned bits in EUI48 as well. For example, the EUI48 address 001122334455 would become 001122FF FE334455 in EUI64. This mapping is the first step used by IPv6 in constructing its interface identifier. So you need, as you can see, for EUI48 to EUI64, it needs to be converted there first before we can construct the IID, or which is the first step used by IPv6 in constructing its interface identifier. When such underlying EUI48 addresses are available, the modified EUI64 used to form IIDs for IPv6 addresses simply inverts the U bit. So again, this mapping is the first step used by IPv6 in constructing its interface identifiers when such underlying EUI48 addresses are available. So this is how the 128-bit address assign it to a link local, or to provide that unicast address to the device. So these are the first step, the EUI48 address converted to 64 and then forming the IID for IPv6 addresses simply by inverting the U bit. So to form the 64-bit IID, you need to be able to invert the U bit from this conversion. When an IPv6 interface identifier is needed, or IID is needed for a type of interface that does not have EUI 48-bit address provided by its manufacturer, but has some other type of underlying address like AppleTalk, the underlying address is left padded with zeros to form the interface identifier. If the interface identifier is needed for a type of interface, or a type of the interface that does not have EUI, so if the interface in the network device does not have this EUI 48-bit address in this net by its manufacturer or by the router, but has some other type of underlying address, the underlying address is left padded, or the EUI or the address is left padded with 0 to form the interface identifier. So instead of doing this conversion, EUI 48 to EUI 64, it is left padded with zeros to form another interface. Interface identifiers created for interfaces, for AppleTalk, they just left padded it with 0 if they don't have this EUI 48 and EUI 64. Interface identifiers created for interfaces that lack any form of identifier, like the EUI 48s and EUI64, like the tunnels and serial links that do not have that, may be derived from some other interface on the same node, because we need to be able to get the IAD to form this IPv6 128 bits. So it may be derived from some other interface on the same node that is not on the same subnet. So it could be got from other interface on the same node, but not necessarily need be on the same subnet, or from some identifier associated with the node. Lacking any other options, manual assignment is a last resort, or from some identifier associated with the node that is not on the same subnet, or from some identifier associated with the node. So it could be got from same node, or from interface from the from some other node, or some other identifier that associated with that node. Lacking any other option, manual assignment is a last resort. So example, using Linux ifconfig command, we can investigate the way a link local IPv6 address is formed. So again, it's all about the link local part of this IPv6 address, which needs 64 bits IID. We need to get that from some other interface on the node, or from some identifier associated with the node. As you can see here, we can see how Ethernet's hardware address 003048281989 is mapped to an IPv6 address. So here the H part are mapped into an IPv6 address. First, it is converted to EUI64, forming the address 003048 FF. So here's where it came from. FF FE 2A 1989. So we add or convert it to edu that hardware address. Again, we need to convert the Ethernet or the OUI, right? First byte to fifth bytes. So here we converted that in the real application. So 0030 48 2A 1989 is the hardware address. Now to convert that, you need to add FFFE in the middle. Next, the U bit is inverted, so we need to invert, forming the D value 023048. So we got 023048 FFFE 2A 1989. So here it is 02 or 23048 FF FE2A 1989. To complete the link local IPv6 address, we use the reserve link local prefix FE80. ::/10, see section 2.5. So here's where it came from. FE80, which is a link local, is converted to this reserve no, it's actually reserve address. So together this form complete address FE80 : 230. So as you can see, we invert the it to U bit, EUI60. We convert it to EUI64, convert that to invert the U bit, and then complete it using the reserve link local prefix FE80. So actually, yeah, it is the reserve link or reserve address within IPv6, but it is a multicast. I believe this is not this. Let's delete. Together this form the complete address FE80 : 230. So that's where we get the 230. colon 48 FFFE FE2A 1989, which is this. So the presence of the slash 64 is the standard length used for identifying the subnetwork or host portion of an IPv6 address derived from IID as required, because it's a 64 bits, and also it's a use for identifying subnetwork or host portion. Another interesting example is from Windows system with IPv6. In this case, we see a special tunnel endpoint which is used to carry IPv6 traffic through networks that otherwise support only IPv4. So there's a tunnel endpoint which is used to carry IPv6 traffic through networks that otherwise support only IPv4. So it's kind of like converting the IPv6 to IPv4 again. So it's in a Windows system. In this case, we see a special tunneling interface called ESATAP. The so-called physical address is really the hexadecimal encoding of an IPv4 address 00998D87. So it just converted the IPv4 address or the 0A998D87 physical address are just a hexadecimal encoding of the IPv address 0A IPv4. So remember, we're trying to connect the IPv6 in this network, IPv4 network. So we will have to convert that IPv4 to an IPv6 to talk to it. So it's actually the same as 10.153.141.135. Here the OUI used is 00-00-5E. Is the one assigned to the IANA. It is used in combination with the hex value FE. Indicating an embedded IPv4 address to form an IPv6. So as you can see here, 00005E. Here it is. And then you need to add FE, indicating an embedded IPv4 address. This combination is then combined with the standard link local FE80, which is this. So as you can see, this hex is converted to 5EFE, which is additional combined with the standard link local prefix. So this FE80 : /10 is a standard link local prefix, kind of like what we did here. It's a reserved link local prefix for standard IPv6 address. To give the address FE80 : 5EFE : 10.153.141.135. So this is where we get here. We convert this to hexadecimal, which is just 10.153, and then convert the OUI. So we did a lot of conversion here. The %2 appended to the end of the address is called a zone ID in Windows, and it indicates the interface index number on the computer. So it is the interface index number on the computer corresponding to the IPv6 address. IPv6 addresses are often created by a process of automatic configuration, a process we discuss in more detail in Chapter 6. So these are actually usually being created using an automatic conversion or algorithm, because imagine like you have to convert this in your router, right? So this is actually how it is being converted under the hood. Let's say you want to connect convert the IPv4 to IPv6 to be able to support that IPv6 to in an IPv4 network. And also as well as this, the conversion in Linux ifconfig, this conversion is being done now automatically by the router. CIDR and aggregation. In the early 1990s, after adoption of subnet addressing to ease one form of growing pains, the the internet started facing a serious set of scaling problems. Three particular issues were considered so important as to require immediate attention. First, by 1994, over half of Class B addresses had already been allocated. So the Class B has been allocated. It was expected that the Class B address space would be exhausted by about 1995. The 32-bit IPv4 address was thought to be inadequate to handle the size of the internet anticipated by the early 2000s. The number of entries in the global routing table, one per network number, about 65,000 in 1995, was growing. So again, the number of entries in the global routing table, one per network number, is about 65,000 in 1995, was growing. So that the routing table, we're gonna solve this routing table via aggregation and a special tree structure. As more and more class A, B, and C routing entries appeared, routing performance would suffer because of the too much table entry. So this requires a long-term solution, which is the IPv6 solved for. And this class B will be solved by using CIDR aggregation. So in order to help prefixes, in order to help relieve the pressure of the availability of IPv4 addresses, especially class B addresses, the class full addressing scheme was generalized using a scheme similar to VLSM, and the internet routing system was extended to support classless interdomain routing. Or CIDR. So again, in order to help relieve the pressure on the availability of IPv4 addresses, especially class B addresses, the classful addressing scheme was generalized using a scheme similar to VLSM, the variable the VLSM we discussed earlier or in the previous video, which provide like a more fine-grained allocation of networks and hosts. And the internet routing system was extended to support classless interdomain routing. So these are the CIDR. It requires the support of a internet routing, which is the IANA, or at the top router. So it's kind of like in OS where you need to support from the internet or the OS and hardware. Here you need to support from the top router to be able to support CIDR. This provide a way to conveniently allocate contiguous address ranges that contained more than 255 hosts but fewer than 65,536. So you can now configure whether it's 256, whether 30,000, 20,000, 15,000, 5,000. That is something other than single class B or multiple class C network numbers could be allocated to sites. So again, that is something other than single class B or multiple class C network numbers could be allocated to sites. So a single class B, again, the earlier the number, the higher host you can provide. So for single class B, other than single class B or multiple class C network numbers like that could not be allocated, right? Because it's a huge host. Using CIDR, any address range is not predefined as being part of a class but instead requires a mask similar to a subnet mask, sometimes called a CIDR mask we discussed in the previous video. CIDR masks are not limited to a site but are instead visible to the global routing system. So these masks, similar to subnet masks, are visible now to the router or global router. Thus, the core internet routers must be able to interpret and process masks in addition to network numbers. So aside from network numbers, which used to define the classes, class A, B, C, you also need this mask. This combination of numbers called a network prefix is used for both IPv4 and IPv6 address management. So this combination of CIDR mask and the network are called network prefix. Prefix is now used for IPv4 and IPv6 address management. Such groupings are now commonly expressed using a prefix of the address space. So an n bit prefix is a predefined value for the first n bits of an address. Now this is the one used in modern internet because such groupings are now commonly expressed using a prefix of the address space. Sir, palagay na lang po dyan. Opo. Thank you. So again, the value of n, the length of the prefix, is typically expressed in the range of 0 to 32, of course. For IPv4, 0 to 128. For IPv6, it is generally appended to the base IP address following a slash character. So this is where the n bits came, the slash, the slash 64 slash 10 you see. Table 2.6 gives some example of prefixes and their corresponding IPv4 or IPv6 address ranges. So here slash 27 slash 32 slash 10 slash 32 etc. In the table, the bits defined and fixed by the prefix are enclosed in a box. So these are the bits, the slash 1, the slash 24, and it's fixed by the prefix are enclosed in a box. The remaining bits may be set to any combination of zeros and ones, thereby covering the possible address ranges. So these define the possible address. So instead of the classes organization, we now have this prefix, which is a combination of really a mask and the network. So this and zeros define the possible address ranges. Clearly, a small prefix length corresponds to a larger number of possible addresses. In addition, the earlier classful addressing approach is easily generalized by this scheme. For example, the class C network number 192.125.3.0 can be written as the prefix 192.125.3.0 slash 24. So the classes could be inside one of these prefixes. So class full A and B network numbers can be expressed using /8 and /16 prefix lengths respectively. So that n bits, like provide um, the /8 and then /16, and those are expressed as integers in the range of 0 to 32 because the max is 32. So aggregation, that's how we provide a prefix for the CIDR aggregation, or the new way to subnet the internet or the networks to provide more configuration for networks and hosts. Aggregation, removing the classful structure of IP address, made it possible to allocate IP addresses blocked in a variety of sizes. Doing so, however, did not address the third concern from the list of problems. It did not help to identify the number of routing table entries. So, alright, reduce the number of routing table entries. So, this where the tree structure that I was talking about. So, a routing table entry tells a router where to send a traffic. So, those prefix solve the first problem. The class B do not have that enough. So using this prefix, now you can now use either one of those prefix for your allocation of unicast address. Now the new problem is the table entry, because you have kind of like in a car, you have multiple entry to go through, which is provides a lot of overhead before you can get to your destination. So we need to reduce that as well. That's the problem 3. And the second one is more long term. It was solved by the IPv6 since it has a lot of possible addresses. So a routing table entry tells a router where to send traffic. So this router table entry tells the router where to send the next hop on the traffic. So essentially, the router inspects the destination IP address in an arriving datagram, finds a matching routing table entry, and from the entry extracts the next hop for the datagram. This is somewhat like driving to a particular address in a car, and in every intersection along the way, finding a sign indicating that what direction to take to get to the next intersection in the way to the destination. If you consider the number of signs that would have to be present at every intersection for every possible destination neighborhood, you get some sense of the problem facing the internet in the early 1990s. At the time, few techniques were known to dramatically reduce the number of routing table entries while maintaining shortest path routes to all destinations in the internet. The best known approach was published in a study of hierarchical routing in the late 1970s by Kleinrock. They observed that if the network topology were arranged as a tree 1 and addresses were assigned in a way that was sensitive to this topology, very small routing tables could be used while still maintaining shortest path routes to all destinations. So as you can see, it's kind of like the binary, heap binary tree. So as you can see, all the left side are lower than it and all the right side is greater than it. So in a network with tree topology, network addresses can be assigned in a special way so as to limit the amount of routing information state that needs to be stored in a router table entry. If addresses are not assigned in this way, left side shortest path routes cannot be guaranteed without storing an amount of state proportional to the number of nodes to be reached. So for here, you only need 9 entries. Here, you need 3 entries to store that to get to your destination. While assigning addresses in a way that is sensitive to the tree topology save state, If the network topology changes, reassignment of address is generally required. While it is more efficient in saving state, if the network topology changes, a reassignment of address is generally required. The root or top of the tree on the left is the router labeled 19.12.4.8. In order to know a next hop for every possible destination, it needs an entry for all routers below in the tree, like 190.16.11.2 here. So to get to the next hop, it needs to save the state for all the routers below it instead of the just left and right. Because here you can just create an algorithm that if it's less than 19.10 or if it's greater than, then you put that into the right side. So for any other destination, it simply routes to the cloud labeled other parts of the network. In contrast to the right of the root of the right hand tree is labeled 19.0.0.1 and requires only 3 entries in its routing table. Note that all of the routers on the left side of the right tree begin with the prefix 19.1 and all of the right begin with 19.2. Thus, the table in router 19.0.1 need only show 19.1.0.1 as the next hop for any destination starting with 19.1. It's actually not using less than, sorry about this. It's a binary heap, but it knows if it's starting with 19.1, so it has that. It's kind of like using an algorithm or code here as well if equals to 19.1, whereas 19.2.01 is the next hop for any destination starting with 19.2. Any other destination goes to the cloud labeled other parts of the network. This results in a total of 3 entries. In the internet context, the hierarchical routing idea can be used in a specific way to reduce the number of internet routing entries that would be required otherwise. So again, in the internet context, the hierarchical routing idea can be used in a specific way to reduce the number of internet routing entries that would be required otherwise. As you can see, it only has it only needed 3 entries. This is accomplished by a procedure known as route aggregation. So to be able to use that context or tree topology in the internet context, we need to use the route aggregation. So this is where the concept of aggregation works. It works by joining multiple numerically adjacent IP prefixes into a single shorter prefix called an aggregate or summary that covers more address space. So this is where we apply that in the actual internet prefix or CIDR prefix we use today. In this example, the arrows indicate aggregation of 2 address prefixes to form one. The underlined prefix are additions in each step. In the first step, 190.154.270 /26 and 190.154.27.64 /26 can be aggregated because they are numerically adjacent. But 190.154.127.192 /26 cannot. With the addition of 190.154.27.128 /26, they can all be aggregated together in 2 steps to form 190.154.27 /24. With the final addition of the adjacent 190.154.26 /24, the aggregate 190.154.26 /23 is produced. We start with 3 addresses prefixes on the left in figure 2.9. The first two, 190.154.27 /26 and 190.154.27.64 /26 are numerically adjacent and can therefore be combined or aggregated. The arrow indicates where aggregation takes place. The prefix 190.154.27.192 /26 cannot be aggregated in the first step because it is not numerically adjacent. When a new prefix 190.154.27.128 /26 is added, underlined, the 190.154.27.192/26 and 190.154.27.126.128 prefix /26 prefix may be aggregated, forming 190.154.27.28 So basically, just look at the graph, guys. This is how it is aggregated. So here, special use addresses. Both the IPv4 and IPv6 address space include a few address ranges that are used for special purposes and therefore not used in assigning unicast address. For IPv4, these address spaces are given in table 2.7. So for all the things like the link local, the EUI, those are just all for unicast assignment of unicast addresses in the network using your router. So again, the EUI or the IPv6 translation are being done by your router. Again, we're talking about the network layer here. So here, as you can see, we have this special use prefix 000/8 host on the local network, 10.000/8 address for private networks or intranets. There's also internet host loopback address, link local address used only on a single link and generally assigned automatically. Address for private networks, intranets such as addresses never appear on the public internet. IETF protocol assignments or IANA reserved. Testnet 1 addresses approved for use in documentation. These addresses used for 6 to 4 relays. Anycast addresses, address for private networks, intranets. Such address never appear on the public networks, etc. Right? So in IPv6, number of addresses range and individual addresses are used for specific purpose as well. They also have this special address. It is listed in this table for both IPv4 and IPv6. Address ranges not designated as special, multicast, or reserved are available to be assigned as unicast address. So here we have /:/0 default route entry not used for addressing //128 the unspecified address may be used as a source IP address. FF00::/8 IPv6 multicast address. So some unicast address space prefixes 10/8 172.16/12 and 192.168/16 for IPv4 and FC00::7 is reserved for building private networks. Addresses from these ranges can be used by cooperating hosts and routers within a site or organization, but not across the global internet. Thus, these addresses are sometimes called non-routable addresses. The management of private non-routable address space is entirely a local decision. The IPv4 addresses are very common in home networks and for the internal networks of moderately sized and large enterprise. They are frequently used in combination with network address translation. So for this non-routable are frequently used with NAT or network address translation, which rewrite IP addresses inside IP datagram as they enter the internet. So when we say non-routable, it cannot route to the internet, only within the network or router network. Addressing IPv4/IPv6 translators. In some networks, it may be attractive to perform translation between IPv4 and IPv6. A framework for this has been developed for unicast translation, and one is currently under development for multicast translation. One of the basic functions is to provide automated algorithmic translation of addresses using the well-known IPv6 prefix 64:FF9B:/96 or another assigned prefix. Specify how this is accomplished for unicast addresses. So this scheme make use of a special address format called an IPv4 embedded IPv6 address. This type of address contains an IPv4 address inside an IPv6 address. It can be encoded using one of 6 format based on the length of the IPv6 prefix, which is required to be one of the following: 32, 40, 48, 56, 64, 96. So there are the examples. For 32, we have IPv6 prefix 32 bits, IPv4 address 32 bits, and you have fixed U bits from 64 to to 70. And suffix 56 bits. For 40, IPv6 prefix 40 bits, IPv4 24, and you have U, and you also have suffix, etc. Right? So figure 2.10 IPv4 addresses can be embedded within IPv6 addresses, forming an IPv4 embedded IPv6 address. 6 different formats are available depending on the IPv6 prefix length in use. The well-known prefix 64:ff9b:/96 can be used for automatic translation between IPv4 and IPv6 unicast addresses. In the figure, the prefix is either the well-known prefix or a prefix unique to the organization deploying translators. So again, in the figure, prefix is either the well-known prefix or a prefix unique to the organization deploying translators. Bit 64 to 71 must be set to 0 to maintain compatibility with identifiers specified in RFC 429. The suffix bits are reserved and should be set to 0. The method to produce an IPv4 embedded IPv6 address is then simple. Concatenate the IPv6 prefix with a 32-bit IPv4 address, ensuring that the bits 63 to 71 are set to 0, inserting if necessary. Append the suffix as 0 bits until 128-bit address is produced. So that's the suffix bits until the 128-bit is produced. IPv4 embedded IPv6 address using the 96-bit prefix option may be expressed using the convention for IPv6 map address mentioned previously, section 2.23 of RFC 4291. For example, embedding the IPv4 address 198.51.100.16 with a well-known prefix produces the address 64:ff9b::198.51.100.16.